Alrighty, hello everyone. Lecture 12, which we're going to recap some ideas on parallel and perpendicular acceleration and how that changes the velocity vector. We've already seen this a couple times already. We did some stuff in the in-class session on vectors related to this as well. But we're going to, again, just kind of finalize it because these sort of conceptual ideas on how you get vectors to change both length and direction are important to remind ourselves of. And then we are going to do circular motion for today. So my question to you is, suppose I have these 6 cases below. Each of them has an acceleration that the object is experiencing, and all the accelerations are roughly the same in each. But each of these 6 cases has a different velocity vector. And the question you should pause and think is, which of these results in the velocity vector changing magnitude, so getting longer or shorter, and which result in the velocity vector changing direction? You can think back to the vector in-class assignment where we looked at vectors that pointed both parallel and perpendicular, and different results occurred. All right, so let's think about these. So in case A, this looks kind of close to 1D motion. In 1D motion, I think our intuition is now on the right track of understanding if I have a velocity vector and an acceleration vector pointing in the exact same direction, that is going to result in the object speeding up. Or vector-wise, the velocity vector will get longer. In the case of A, it is more or less pointing along the same direction as the acceleration vector. So I would say that this will, the length of the vector will increase. But since they are not perfectly parallel to one another, remember the acceleration vector wants to try to make the velocity vector point parallel to it. Since they're not initially parallel, this will also result in a direction change. The velocity vector might get pulled down to point a little bit more. Right now it's kind of pointing at a 45-degree angle. It might be pulled down to point more at like a 40-degree angle. For B, they are drawn anti-parallel to one another. So this is just a simple 1D problem. But in this case, the velocity is pointing, if I tilt my head, the velocity is pointing to the left while the acceleration is pointing to the right. In that case, we saw that this results in V changing. This might be a case of, say, your car slowing down. The velocity vector is going to get smaller. In terms of direction change, the velocity vector is not going to start sweeping in two dimensions, but I suppose it is possible if the acceleration vector is strong enough that the velocity might flip over and point in the opposite direction. So V could flip if A is large enough, or given enough time. So I would say this is likely just a case of slowing down. If the acceleration is large enough or enough time passes, this might be not just slowing down, but slowing down, coming to a stop, turning around. All right, C. The velocity vector and the acceleration vector are almost perpendicular to one another, but not quite. The angle between them is less than, this angle is less than 90 degrees. So if I were to say, is the velocity vector pointing in the same direction as A, perpendicular to A, or anti-parallel to A, it's closer to pointing in the same direction as A. So again, that then follows that they're both pointing more towards the same direction. I would say V will increase. And again, change direction. the velocity vector will grow and try to point more in the direction of A. Contrast that with D, where now the angle between them is greater than 90 degrees. So it looks like the velocity vector is closer to pointing anti-parallel to A compared to parallel. So they're closer to being like this, where like in part B, we saw that is the case where V shrinks and also changes direction. A is going to try to pull V to point in the same direction. V will have to decrease first. It may eventually flip around. And then just skipping to the other, skipping to F, which is kind of the same sort of setup as D. But now we have this case E, where they are perpendicular to one another. So V is neither pointing in the same direction as A or anti-parallel to A. So in this case, this might be the one where it was kind of uncertain. This one is the case where V, the magnitude of V, does not change. It simply changes direction. In this case, the acceleration is going to try to pull the velocity to point towards the upper right. But at this given moment where they're exactly perpendicular to one another, the length of the velocity vector will remain the same length. So I could try to generalize this. Suppose I have some velocity vector, and I'll draw it like this in the horizontal direction. And I additionally have some acceleration vector, which might point like this. And I could ask, how do I expect V to change as a result? And what parts of A tell me how V is going to change? I could think of this as an axis system where I put the axis along the same direction as V. So V is kind of playing the role of the horizontal axis in this case. In this case, just like we did when we looked at, say, the components of a vector, where some part was pointing in the x direction, some part was pointing in the y direction, I could do the same sort of thing, but instead of saying x and y, I could say something like there's a part of the acceleration vector that points in the same direction as V. And there's a part of the acceleration vector that points perpendicular to V. So there could be this component here, which is, I could call it A parallel. The part of A that is parallel to V. And then there's this part of the vector, I could call it A perpendicular. The part of the vector A that is perpendicular to the velocity. So this is the parallel component. And this is the perpendicular component. Now, the parallel component, that is the part of the vector that points in the same direction as V. So there, again, we have the 1D problem. Since they're pointing in the same direction, that would tell me that the velocity vector is going to get larger, or the object is going to speed up. Compared to the perpendicular part of the vector A perpendicular, that part is not going to change the velocity vector's length or magnitude, but it will change the direction. It will cause the object to start to rotate towards that perpendicular component. And again, it doesn't have to be a nice axis like what I just drew, where it's horizontal and vertical. Right? I could have this be my velocity vector, and suppose this is my acceleration vector. I could imagine this as, my textbook is in the way. I can imagine this as an axis that is along V, and then an axis that is perpendicular to V. And so as a result, there is a part of A right here, we'll call this A perpendicular, and there's a part of A that is A parallel. And the main takeaway here is that A parallel is telling you how the magnitude changes. A perpendicular is telling you how the direction of V changes. And I did this with acceleration and velocity. I could have also done this with position and velocity. The velocity, there could be a component of the velocity parallel to the position vector and then perpendicular. And it's also saying something about how the position is changing both in magnitude, the magnitude of displacement, and the direction that the object is moving in. But since in this class we are going to ultimately be more focused on accelerations, in 2 lectures we will start being really focused on accelerations because they are what tie forces to motion. I think it's better to think of this in terms of the velocity and the acceleration. There's a horizontal component and a vertical component relative to that vector, and those 2 components are telling you how the vector changes. Remember, a vector is both a magnitude and a direction. So a vector can change either by changing its magnitude or changing its direction. This is giving you how that is accomplished. The parallel component changes the magnitude. The perpendicular component changes the direction. I think that's even worth a highlight. We'll just highlight this entire thing. And aside with this, I could think perhaps for those who like to think a little bit more mathematical or quantitatively. You could prove this, for example, with the projectile. You could take a projectile which is launched, goes up, reaches some max height, falls back down. We've now solved many problems doing that, where I could write some coordinate axis with a positive x and y direction. And I could look, say, at different points and draw out the acceleration and the velocity. The velocity is just tangent to the curve, so it looks something like this. Those are the velocity vectors. And the acceleration in this case, again, is just gravity pulling down in the vertical direction. So each of these actually have the same acceleration vector that just points straight down. Assuming we're on the Earth, that vector has a magnitude of 9.8 meters per second squared. So if I look at these vectors, I can see that sometimes the velocity and acceleration are pointing kind of away from one another. Sometimes there's one case they're perpendicular, and there's one case where they're pointing more parallel to one another. So if I called these cases, say, 1, 2, and 3. Case 1, it looks like I have something that looks like this. So if I were to draw axes kind of along the velocity vector, there is indeed a part of the acceleration due to gravity that points perpendicular, and a part of the acceleration due to gravity that points, in this case, anti-parallel. So this, I would say, it means you're changing direction. Oops, I was going to write delta for change, but then I started writing the word change. So change in direction. And then this part here is change in magnitude. In this case, it is slowing down because the acceleration and velocity are pointing anti-parallel to one another. And then similarly at point 3, it's the same idea, but flipped. In that case, the acceleration vector has a part that's perpendicular, so it's changing the direction of the trajectory. It's not moving in a straight line, it's this parabolic shape. And there's also a component of the acceleration that's pointing in the same direction as velocity, which is meaning that the projectile is speeding up, which intuitively makes sense. On the second half of the journey, as it's falling back down, it's indeed speeding up as it falls. Where on the first half of its journey going up into the air, it is slowing down until it reaches the top, where it's at some point, which with two-dimensional motion, the velocity is not exactly zero at the top, because it still has that horizontal component. But if you think of, Calc 1 techniques, you could prove that it's an extremum at the top. That's where the velocity is the smallest, or the speed, rather, is the smallest. And again, if we look at case 2, that is a case where the velocity is pointing exactly to the right, and acceleration is still pointing straight down. And they are at a 90-degree angle from one another. So at that very brief moment at the top, where the velocity and the acceleration are perpendicular to one another, the speed of the projectile is not changing. Only its direction is changing at the top. And if you like and prefer to do something like a mathematical proof, you could look at, say, what is the velocity vector in general? And I'll just write down what the answer is and let you justify with the kinematic equations. The velocity vector in general looks something like this. The horizontal component is a constant. The vertical component has some initial value that changes as gravity continues to pull down, down, and down. It's at the top when this vertical component is zero. It only has that horizontal motion. The velocity vector is horizontal at that moment at the top. So there's no vertical component pointing up or down. So again, the time to get to the top is then something like the y velocity divided by g. And I think we saw that in other problems. But I could ask, again, the claim here is that since they're perpendicular to one another, the magnitude of the vector is not changing. What is the magnitude of velocity? Speed. So I could calculate, for example, what is the speed in general? And that's not too bad because I have the velocity vector already written out. So I can easily just calculate the magnitude of that vector. This would be the speed at any point along the path. Just give me a time, I'll plug that in, and that tells me the speed. Again, notice if you plug in t top, as I called it, this just becomes the horizontal velocity component, because that thing in parentheses goes to zero. And I'll leave this to you if you feel inclined. You could ask, how is the length of the vector, or the magnitude, or in this case the speed, changing? So you could calculate, for example, the velocity, or the derivative rather, of the speed, and show it equals zero at t-top. So take this massive square root ugliness, take the derivative, plug t-top into that expression. You should see, if you did it correctly, that it is identically zero. Again, meaning that at that brief moment at the top, the speed or the length of the velocity vector is not changing at all. In order to do that, you need the chain rule. So if you haven't seen the chain rule yet, table this for now and give it a shot if you feel inclined at some future point. Or forget that I ever said any of that. All right. Now let's think of a different case. Projectile motion we were thinking of a case where the acceleration vector was a constant. In the case of projectile motion on the Earth, the acceleration vector was a constant that had no horizontal component and a constant vertical component. The acceleration always pointed down with a length of 9.8 meters per second. It was constant both in direction and in magnitude, hence the kinematics equations were able to be used. Let's consider a different scenario, not projectiles, but just ask, what if the acceleration vector is always perpendicular to the velocity vector? And we could think, what does that mean about how the velocity vector is changing? We just talked about how perpendicular components don't change magnitude. So in this case, the velocity vector should not be getting larger or shorter. But perpendicular components do change direction. So this might be a case where the velocity is continually changing direction. And we could do this on a computer, but I think if we just sketch out a couple examples, you'll see kind of what sort of motion this is going to be. Of course, the title of the lecture might be a hint as well. So suppose I have some point and it has some velocity that is initially pointing in this direction to the right. And I tell you that the acceleration is always perpendicular. So in this case, the acceleration might be something like this. The acceleration vector is going to want to pull the velocity vector to point in the same direction. So as a result, the velocity vector is going to want to be pulled downward. I need another pen. I need colored pens. We'll use these so I can stick with green and red as my velocity and acceleration. All right, so you have your velocity vector that's initially perpendicular to the red acceleration vector. As a result, this guy gets pulled down towards the acceleration vector. Now, if the acceleration vector just stayed like this forever, indeed, given enough time, eventually the velocity would also be pointing in the same direction. Like, say, a projectile. But this is not a projectile. We're saying that these two guys are always perpendicular to one another. So as this gets pulled down, the acceleration vector also changes. Then it gets pulled down some more, the acceleration vector changes. So the velocity is always trying to catch up to the acceleration, but the acceleration is always turning so it remains perpendicular to the velocity. So for example, it might kind of rotate, it might, it's initially going to the right, but then it might get pulled down. So then the point might eventually be here. The velocity vector is now pointing like this, but the acceleration vector has adjusted, so it's still perpendicular. The position adjusts itself again. Velocity is now pointing down, because again, it's trying to point in the same direction as the acceleration vector, but now the acceleration vector is pointing to the left. So as a result, the velocity vector tries to also point to the left. So I think it's just something like this. I think you see where we're going here. But now acceleration adjusts. Yada, yada. Yada, yada. Blah, blah. Blah, blah. All the while, acceleration points inward. So what does this look like? This looks like a circle. So this is circular motion. If the acceleration remains perpendicular to the velocity, you can get what is actually more specifically called uniform circular motion, where the object is moving not only in a circle, but is moving at a constant speed. Again, a result of the fact that the acceleration is perpendicular to velocity. So let me write this down. So we will be most interested in something called uniform circular motion. Can you get motion that's circular but not uniform? For sure. Tends to not actually be circular in those cases. It tends to be more elliptical. The orbits of, say, Pluto and Mercury, for example, are ellipses, a result of this not quite perfectly uniform circular motion. But we'll stick with uniform circular motion, which I'll define as an object moving in a circular path at a constant speed and at a constant radius. That last point is a little redundant because I called it a circle, but yeah. So in this case, I could say that the vector v is always changing direction. But the magnitude is a constant. Or if I wanted to be mathy, I could say the derivative of the speed is always 0. Since v is changing how? Only changing direction. But nonetheless, that means the velocity vector is changing. What does it mean that, what is required for a velocity vector to change? There is an acceleration. Now I'll call it a vector, but I'll put a little c under it. That is always perpendicular to v. This center seeking, and you can see from the drawing, this acceleration always is pointing towards the center of the circle. So sometimes it's called the center seeking acceleration. Points toward the center of the circle. My penmanship is not good today. I'm sorry. Center of the circle. This acceleration is also called the centripetal acceleration. Centripetal acceleration. So I will try to keep personally with the convention that if I write down an acceleration with a little c as a subscript, I'm talking about a centripetal acceleration or something regarding uniform circular motion. Now you could also ask, perhaps that felt a little hand wavy. I kind of just argued, using kind of a very cutesy example, and I just claimed the acceleration must point towards the center. We could also do this on a computer and see what is going on as well. So in this case, I've just drawn a circle, and we're going to assume that the motion is circular and uniform. So if you were to describe the position, say, of a particle that as it moves in uniform circular motion, if I put the origin at the center of the circle, which would be a good choice, then describing the motion would just be tracing out a circle that has some given radius. In this case, it looks like I used 4 as the radius. Just by looking at the motion of this image, we could ask, what direction does the velocity point in uniform circular motion? I'm actually going to ask you to think about that here. The instantaneous velocity of a particle, suppose I tell you it's 2 meters per second, comma, negative 2 meters per second. And that is the instantaneous velocity as the particle moves. The particle, I tell you, is moving clockwise around the circle. If the particle is moving clockwise around the circle, and that is the velocity vector, which of these 4 quadrants is the particle located in? So if I look at this velocity vector, the x component is positive. So though I did not put arrows, admittedly, on my coordinate axes, we'll take to the right as positive, to the up as up as positive. So in this case, I would say the velocity vector points to the right and down, since the y component is negative. So it points, if I go back to my board, I would say that the velocity vector might point something like this. It points to the right, which is positive in the x direction, and down because it's negative in the y direction. So if the particle is moving around the circle, I might say if it starts here, then it's here, 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 etc. It is moving clockwise around the circle. So I would imagine that the velocity might look something like this as it moves around. In which case, then I would say, a point like right here might be correct. So I would say that it was in quadrant A. Okay, so we could go back to my computer image and we could look at what the velocity vector looks like, though admittedly I should have made the example consistent. This particle is moving in the counterclockwise direction. So as the particle moves around the circle, you can notice that the velocity vector is always tangent to the direction that it's moving. The velocity vector points along the circle. Then I have this design so I could consider 2 different points. So I can consider a point at some earlier point in time, that's red, and then some point at some later point in time, blue. And you can see that as time moves forward, you're essentially tracking, a displacement as the object moves around the circle. And if I wanted to talk about something like the acceleration, we defined acceleration as the displacement in velocity, so delta v final minus v initial, divided by the amount of time that's passed. So I could calculate by hand, by a computer, what is the difference in these 2 velocity vectors. They're both the exact same length. That was the assumption. The velocity is not changing in magnitude, but they're clearly pointing in different directions. I can make it even more extreme. In this case, one vector is pointing up to the left, and this vector is pointing down to the left. So the velocity vector is clearly changing. I could take the vector difference of the 2, the final vector, subtract from it the initial vector. I could look at the individual components, subtract the x components, then subtract the y components. That resulting vector would be it would point at least in the same direction as the acceleration vector. Doing this on a whiteboard is next to freaking impossible. Because if you don't do it exactly right, you could actually end up reaching the wrong conclusion. Which is why, again, I like computers in this case. So I'm going to do it on a computer where I have 2 points with 2 different velocities. And this red curve that you're seeing is plotting the difference between the 2. Don't think I'm trying to fool you here or that I'm cheating. I'm not just drawing the red arrow to point in the right direction. The computer here, you can't really tell that that's what's going on, but in this madness, I am saying, here are the 2 velocity vectors. Now do a vector subtraction and plot that as a red arrow. So as I change what the 2 green vectors are, the program auto-updates what the difference is. And you can see actually in the nice kind of clean case of a circle, you might have thought we would have had to take some sort of limit as the 2 points get closer and closer and closer to one another. And to get the right magnitude, you do. But to get the direction, I could have these 2 points widely separated from one another. And even as long as they're on the circle and they have the same magnitude, both arrows are exactly the same length, their difference always points exactly towards the center of the circle. And if I make the 2 points closer and closer to one another, the acceleration continues, of course, to point towards the center of the circle. And then it also gets the appropriate magnitude as well, which we will now consider in a second. So this is center-seeking motion, an acceleration that always points towards the center of some circle, and your velocity is restrained to always be perpendicular to the circle. In that case, as a result, since they're perpendicular, the velocity does not change in magnitude, but it is always changing in direction. What is going on when I spin this? What I'm doing, we haven't done forces yet, but what I'm doing is I'm connecting the ball by a string in my hand. So the string is actually what is providing an acceleration, is pulling the ball towards the center of the circle. So the ball feels an acceleration towards the center of the circle, but it is constrained to kind of move in a circle because I'm spinning it. And as a result, it spins in a circle at a roughly constant velocity in this case. So that's the idea with circular motion, conceptually. But now we get to ask, what is the magnitude? What is the magnitude of this centripetal acceleration? Your book goes through the mathy version of this derivation. So I'll let you just look at the book at your leisure to get the math proof of this. I'm going to motivate the answer through dimensional analysis. Dimensional analysis, it's a highly effective tool if you just want to get a feel for how one variable might scale with the other. Like, does this acceleration is it proportional to the velocity, or the velocity squared, or the square root of the velocity? And dimensional analysis, is analyzing the dimensionality, or in this case, the units. So when you have kind of a well-stated problem, that is not a circle. That is also not a circle. I give up. Pretend that's a circle. When you have something that is constrained to move in a circle at a constant velocity, there are well-posed variables that define the system. It's a circle, and a circle is defined by its radius. That's the only thing I need to know. If I want to draw a circle, all you have to tell me is the radius. And the object is also moving at some constant velocity, v. Or I'll write underneath it. The magnitude is a constant, which in this case I'm just going to write as v without the little arrow, which I think matches what your book does, though I, again, prefer to make sure I'm thinking about things in terms of vectors and magnitudes. But I could write this as kind of the absolute value of the vector, or just write as v, like your book does. And if I think, are there any other variables, parameters, whatnot that I need to know to actually solve this problem? And there's not. This has nothing to do with gravity, so I do not expect, say, little g to be anywhere in the answer. This has nothing to do with, say, quantum mechanics, so I do not expect Planck's constant h to appear anywhere, which is kind of the fundamental constant of quantum. Like, there's no electrons, so I don't expect charges to appear, or, so really r and v are the only kind of parameters of this problem. And so I could ask, what combo of v and r give me an acceleration? How do I combine them in such a way so that the unit ultimately ends up being acceleration? Meters per second squared, for example. You could say, is it v times r? Well, the unit of that is the unit of v times the unit of r, which is meters per second times meters. So that would be meters squared per second, which is not acceleration. You think, okay, what if it's just v squared? Maybe r doesn't matter. Well, that's meters squared per second squared, which is not an acceleration, but it's kind of close because acceleration is meters per second squared. So if I got rid of one of those meters, I'd be gold. So you might think, okay, then divide by a length. And guess what? We have a length at our disposal. We divide by r. This is meters squared per second squared, all divided by meters. That is indeed a unit of meters per second squared, which is the unit of acceleration. So without doing any complicated math, just by looking purely at the units, what this tells me is this says the magnitude of the centripetal acceleration must scale as v squared over r. There is some number out front, maybe it's 3, maybe it's pi, maybe it's 1 over 6, which this does not tell me. This only is telling me scaling. Dimensional analysis gives scaling only, in that you actually have to do the complicated math if you want to get the exact number. But it turns out in this case, actually, the constant is just 1. So the answer, when you go through the math, actually is just v squared over r. Or, to use the vector notation, the magnitude squared over r. Tell me it's uniform circular motion. That means there's a constant v and a constant r. I can square the velocity, divide by r. That tells me what the magnitude of the centripetal acceleration is. Then if I want to know the length of the centripetal acceleration, easy. I know it's pointing towards the center of the circle. We will see dimensional analysis again. You can do similar things, for example, with simple harmonic motion and essentially get the right answer. Famous equations, or rather equations that have gotten people's names attached to them, have been first kind of written down through dimensional analysis. One that comes to mind for astrophysics, I guess, is the Kolmogorov power spectrum of space is turbulent and it obeys a certain relationship, which is the Kolmogorov scale. Anyway, which he proved using purely dimensional analysis. Well, he proved what the formula was, rather. All right, how about an example? E.g., whatever. E.g., the International Space Station orbits around the Earth. It moves at about 4.76 miles a second, which is about 7,660.5 meters a second. So it's careening along at a radius of something like 6,778 kilometers. I could ask, what is the centripetal acceleration experienced? Now, one thing I will point out here, again, just to make sure it's crystal clear, is remember this radius is the radius to the center of the circle. So in this case, if I were to draw the Earth, and and then the orbit of the International Space Station. Those are supposed to be concentric, but they are not. So there's the Earth, and then the International Space Station is kind of doing its thing. When I talk about the radius here, I'm talking about the radius of the orbit, which goes, which starts here and goes out to some midpoint here. It is not the same thing as the distance the International Space Station is above the Earth. It's only a couple hundred kilometers above the surface of the Earth. This drawing is actually not drawn to scale at all. It's only about 400 kilometers above sea level. But when I say that the radius of the orbit is 6,778 kilometers, I mean the radius from the orbit to the center of the circle, which is, in this case, at the center of the Earth. So then, this is just the magnitude of the velocity, which is given to us, divided by this radius. I could plug in numbers. I get something like 8.67 meters per second squared. Again, making sure I convert all my units appropriately first. As an aside, note, you could ask, where is it? Right now, again, we're still in the chapter where we're describing motion. We're not explaining motion. So we're describing this motion as it having an acceleration of 8.67 meters per second squared. The reason is, of course, the Earth's gravity is pulling down on the space station and trying to get the space station to fall back down to Earth. But the International Space Station, since it's moving as well, kind of, it's moving around the Earth as well, keeps falling towards the Earth and missing. Notice this 8.67 is not 9.8. It's far enough away from the surface that the acceleration due to gravity is not 9.8. Remember, that's only when you're close to the surface of the Earth. Anyway, end of aside. How long does it take the ISS to orbit around once? This is called the period of an orbit. If I'm talking about the period of an orbit or of an oscillation, I'm saying, how long does it take to get back to where it started? In this case, the period then represents the amount of time it takes to go around the Earth once. So period is the units of period, which your book uses capital T. The units of period, of course, then is seconds, minutes, hours, something to deal with time. Now we could think, how could we calculate this? We could actually derive the formula. Pretty straightforward. It is moving in a circle. It goes around the circle once. It's moving at a constant speed. Constant speed, we saw, there is then a relationship between distance, speed, and time. It's kind of one of the kind of more basic kinematic equations. If I have a constant speed, 30 miles per hour, then every hour I move 30 miles. If I drive for 5 hours, my total distance is my speed times the time. 30 miles per hour times 5 hours, 150 miles. So we can do the same thing here. Since, again, the velocity is only changing direction, the speed is a constant. And if I'm asking for the speed, which is v, and it's going for a certain length of time, which we are talking about one orbit, the time it takes to make one orbit, which we're calling the period, which we're calling capital T. And then what distance is covered here? It goes around the circle once. So this is just then the circumference of the circle, 2 pi r. You therefore get a relationship for the period of 2 pi r divided by v. Again, for uniform circular motion. That is an assumption built into this expression. I should have said that up here too. If I were to, box this. This equation assumes uniform circular motion. If it's not uniform circular motion, you better not be writing a equals v squared over r. Just like how if the acceleration vector is changing, you better not use the kinematics equations. You should think about that. Maybe I'll ask this on a handout, or maybe an exam. Is there ever a case where you can use both the kinematics equations and the uniform circular motion, a equals v squared over r? I'll let you think about that. Anyway, for the ISS, I know the radius of its orbit. I know the velocity. I could plug those in. If you saw the movie Gravity, you might anticipate that the answer is about 90 minutes. It orbits the Earth about once every hour and a half. Which again, it's moving pretty fast. Almost 5 miles every second. These days, running 5 miles kills me. And it definitely does not happen in a second. All right. Where am I in time? Okay, good. Let me just say one more thing. There's another quantity that we will see later in the course. We won't really need it now, but it's related to period. So while I have period here on the screen, I will just define it, and then we'll call it a day. So another quantity we'll see is called the frequency. So we'll see this more for oscillations, which are related to circular motion. So we define the frequency. I like to use lowercase f. Its formula is pretty straightforward. It's just 1 divided by the period. The units of frequency is then the unit of 1 divided by the unit of period. So it's in SI units, it's 1 over second. This pops up so much it has its own name. This is called the hertz. Named after hertz. So 1 over a second, if you say something as 20 hertz, what it means is that there are 20 oscillations or 20 periods per second, for example. So for example, the frequency of the ISS, I said it was 90 minutes. So the frequency was the period, so the frequency would be 1 over 90, minutes to the minus 1 per minute. So the interpretation is that it completes 1/90th of an orbit per minute. Which, again, makes sense. In 90 minutes, it is a full orbit. So in one minute, it accomplishes 1/90th of that. Frequency, you'll see frequency period. They're essentially saying the same thing. But what you write and use, one or the other makes more sense depending on the context. We will see it when we do oscillations. So for example, you go to a piano and you find middle A, pluck middle A. That is defined as the standard from the 19th century, like the Stuttgart pitch, I think it's called, where musicians all agreed that, middle A is going to be defined as 440 hertz. What that means is that it completes 440 oscillations per second. So we'll get to this when we talk about waves. Essentially, a wave that oscillates up and down. Essentially, it does one full oscillation, goes down and then back up, 440 times every second, and that is middle A. All right, circular motion, different from projectile motion, has its own set of assumptions built in. So make sure you understand kind of what is the difference between when we're talking about projectiles compared to when we're talking about circular motion. We will see circular motion a good amount in this class. And you should get in the habit now of thinking, if you see words like uniform circular motion or circular motion with a constant velocity or stuff like that, you should immediately get in your head, sirens and red lights should go off that whenever you're thinking or seeing things like uniform circular motion, A equals V squared over R should pop into your head. If it's not uniform circular motion, V squared divided by R should be the farthest thing from your mind. Because again, the assumptions are not met to use a new formula like that. Alrighty. See you anon.